until the last exam. This is going to take some time. I have to restart and everything. So, but I'm good with all the grading, right? The last exam, exam 3 is graded and everything. The homeworks, every week I do check and I do grade. Sometimes they submit the late. If they submit late, I took out some points. But whatever I had, I'm gonna check again this week. And this is the final week. If I don't get anything after this, then that's it. This is the final week. That's it. Okay. So the only thing I'll be receiving next week is the final exam, which is due on Wednesday. You know that, right? Wednesday is the final exam. It's due on Wednesday. All right. Did you know you listen what I said, right? Okay, that's about the homework. So if you have anything due, you may still submit it. I mean, lose significant amount of points because it's a late submission. And then after this week, no more submission allowed. Okay, when I'm saying this week means Friday. Okay. After Friday, no more submission. No homework submission allowed. Okay, and there's this final exam. I'm putting it record. I probably started talking about it already, but there's this final exam. Let me actually start with this thing first. So we are in chapter 16 today. This is chapter 16. Okay. So I was just talking about the final exam, right? The final exam is take home, as you know already, and I'm gonna upload it. Actually, I already made this question, but I'm gonna make it available to you guys. I'm gonna make it available to you guys on Wednesday, okay, on our class. I think I put no, not Wednesday. No, it's Friday. So I'm gonna make it available on Friday, and then it's due on Wednesday next week. All right. So what I'm planning to upload a video lecture, okay, on Friday because there won't be any Friday class. You guys know that, right? There's no Friday class. So I'm planning to upload a video lecture. So on that lecture, because there is no class, so I got to do something about the class, right? So on that lecture, I'm gonna talk a little bit with the exam. Probably it's the 5 minutes, 10 minutes, 20 minutes. I don't know, depending. Okay. Usually the video lecture doesn't take that long. But how you can reach me because there is no class, so you can obviously reach me in Microsoft Teams, right? If you have any question, okay, uh, with uh, with the missing class, I guess. Uh, and today I'm going to start with this topic. You're going to be seeing it shortly. This was not there, so I have to restart, and it took a little bit time. So I say this is the. You're going to come. Wait, hopefully it is not coming. Sorry about that. Technical glitch. So HDMI. Yep. Sorry. All right. So it is probably the most difficult chapter in this book. Okay, so far whatever we learned didn't go through that much detail on any of this angular motion, right? We did some angular motion, remember, on the swing. Okay, we did some, but not the curvilinear motion. Anybody is familiar with curvilinear motion? We're going to take it lightly, by the way. So max one problem will be seen in the exam, and it's a take home, so it shouldn't be that difficult, right? You can have to deal with that, right? But this topic itself is difficult. Okay, I didn't quite say a difficult thing all through the semester, right? I mean, but this is when comes really understanding issues, right? Because it's a curvilinear motion. It does have the rectilinear motion, and at the same time, it has the rotational motion. So both comes together. The general motion has something like googly all around the places, right? You know what I'm saying? So that's why it's difficult. All right. So we're gonna take it lightly, as I already mentioned. I have only two problems on this chapter that we'll be doing. I mean, after this theory done, possibly I can start with one problem, even maybe finishing up that. Who knows? And in the last class, means in Wednesday, we're gonna do the other problem. Okay. And if we can't finish the today's problem, then we're gonna do like partially this problem and the other problem on Wednesday. So that's the plan. All right, let's move on. So I was just talking about the curvilinear motion. What are the applications for that? Okay, I mean, if I'm gonna see this roller coaster ride, immediately you see the application, right? It does have a rotational motion, right? And it doesn't goes like only like a pendulum, right? It goes all over the places, like magic carpet, all sorts of things you've seen in the roller coaster. It's definitely application of that. Okay, it does have two different kinds of motion. Again, angular motion and the translational motion. Okay, if you combine them together, then this kind of motion will come. And the other applications, obviously, I have few slides here. By the way, these materials I didn't upload it in Brightspace yet. I'm gonna do it today. Okay. Yeah, hopefully. Okay. I won't be giving you any more homework though, right? You guys want another homework on this? Who wants another homework? No. I won't be giving any homework in the last week. Don't want to bombard with you with stuff. Okay, but just tell you this though, the problems that I'm solving here, pay closer attention. Try to understand it as much as you can, and do some more from the book. Everybody have the access of the book. If you just flip through the book, there are so many problems in the examples, right? I don't even tell you like go through the exercise problem. Just flip through the example problems, and these two problems that I'll be doing should be enough to deal with the final one question. All right, so this is another very interesting application. As you can see, you're seeing, I don't know how many of these parts that you are familiar with. Everybody's familiar with gears, right? Pulley. How many of you pulley you are familiar with the camshaft? If you know a little bit with the cars, maybe you are familiar with that, or machine shop. If you ever had exposure or opportunity to see what's happening inside the lathe machine, or all this shaping machine, milling machine, all those machines. You guys all took the machining class, right? Mechanical engineer. Okay, if you are doing 4 years mechanical, you should be taking on machining cars. Like, what is this course called? Manufacturing engineering, if I'm not mistaken, Mech 132 or something. Anyway, so on that course, these kind of things are very very common. All this machine has all those components that you're seeing here, obviously. And the thing that I'm highlighting here, you see, these two are kind of straightforward, gear and pulley, right? Those goes with like rotational motion. Like when it comes to the cams doesn't goes with a straightforward rotational shape. What does it mean? Anybody seen cams before? I mean, when I was in undergrad, we used to have one course that course name is engineering mechanics. That course deals with these cams and this complex and very complex thing, believe me. So the thing that I'm trying to highlight here, though, we're going to touch upon those complex things a little bit. Okay, the dynamics is like the first step of engineering mechanics. That's the advanced course. Okay. Anyway, now coming back to this cams. Cams has this weird shape which can move things not you're seeing, right? So the cams has a weird shape, like kind of like a TV shape. You think that way, right? When it rotates, it doesn't rotate like a perfect circle or something, right? So if something attached to this, say they call link, okay. So if some link attached to connecting rod, sometimes they call connecting rod as well. If a connecting rod sometimes attached to that, right, you're gonna have all sorts of movement like differently. Another example could be like in car, have you ever noticed like the piston is connected with connecting rod and is connected with the shaft eventually, right? And it has all sorts of movement because it's translating the rectilinear motion because the piston is moving up and down, right, on a rotational motion. So that's why this came in play. Okay, and all the machine operates kind of the same way, right? Anywhere you see machine, something is running, the source is a motor, and motor always rotate what? Like a circular motion, right? And you converted that circular motion to all sorts of motion that you desire. Like in a lathe machine, you want to move it like linearly, right? If you have the capability. The shaping machine, you'd like to move it 2D axis, right? So all sorts of move is coming from the motor, and motor is rotating what? Only the circular motion. Okay, so that's why these things are a little complicated. And again, intention here is to just introduce you with these things. In advanced course, you should be learning more. That's the expectation. Or you may actually learn it by yourself as well. Okay. Now there is this actual theory. These beans that you're seeing here, these beans will not going to give you that much of understanding, but it will going to give you like the practical application wise. It will going to give you the overview what kind of motion we're talking. So path of a rectilinear motion is very straightforward. If you're going to think these two dot point, right? And this first one is corresponding to the first one. I mean, I should say top one. The top on the left side is corresponding to the top on the right side. The same thing is top on the bottom side. top on the bottom side, okay, right and left. So that's the rectilinear motion, as if like you are walking in a plane surface, right? And the curvilinear motion means if you have a curved motion, means like the top one and the bottom one, if you're going to connect them, it would be a straight line. But if the rotation is moving along 360, it won't be a straight line. That explains that. So basically, there is a curve involved. Okay, and then this rotation around a fixed axis. Okay, that's another kind of motion. So how many motions that we understand? The straight rectilinear motion, okay, the curvilinear motion, it follows a line. Linear means line, but in a curved way, right? And a rotation around a fixed axis. If you're going to add them, all three of them together, you'd be seeing a general plane motion. You see, the beams are everywhere. Okay, not necessarily it's just moving, both like the rectilinear and the curvilinear motion, it's also rotate, it's an on axis. Is got it? Not that much difficult, at least up to this point, I would say. There is this definition of what I was just saying. Like, I don't want to bore you with the definition. You understand it, right? What was showing in the figure, right? The curve motion and the straight or rectilinear motion. Okay, rectilinear motion is like as if like you are walking in a straight plane. All right, then this thing, rotation about a fixed axis, that's the third one, remember. And final explanation is the general motion, which is the combination of all those things, especially the translation and rotation. Now, under this translation, remember, what are the different kinds of translation? Two different kinds. What are them? One is the rectilinear, another one is the curvilinear, right? Makes sense? So it could be either one. Bottom line, you will have the translation and the rotation. Okay, so now there is a very interesting example here that you're seeing. This is one of the example that you're seeing. Say like this could be considered as a piston cylinder assembly, like inside a car, right? Pretty much everywhere we use the pistons in generator, car, Honda, bike, whatever you want to say. So the movement, the linear movement of the of the piston inside the cylinder, we're going to translate eventually to some different motion here. Obviously, we are seeing here we have a rotor, or you can say like a disc or something, whatever is attached here. So this motion is conveyed here with this disc in a rotational motion. So you see, this rotational motion is about a fixed axis. This is the fixed axis motion, right? And then ultimately it comes here where there is another fixed axis, right? And this translation happen on this connecting rod. They call this thing connecting rod. Curvilinear translation. Why? Because you see, this thing will gonna move around this circle, right, all over the places, and this motion, because of this axis, this disc movement will gonna be looks like a curvilinear motion. Maybe like it will gonna go like this, like this, like this, like this. So if you're gonna add those dot, you see there is a curvilinear motion. Make sense? All right, so all the explanations are here, and these are theory only. When the math will gonna come, you'll feel more excited, I know, but please read through that. As I said, I'm gonna upload all those theory in Brightspace. Okay, all the slides that you're seeing here up to chapter 15, whatever I finish up until last class, all the materials are in Brightspace. Everybody checked it, right? Everything is in Brightspace. Okay, this is the new material I started. I'm gonna put it in Brightspace. All right, so from here, we are slowly jumping into the math portion, okay? So far, it's like all words, no math or nothing. Let me go my class note, okay? Just 1 second. All right, so what we're trying to understand here in these slides, so rigid body motion translation, okay? And if these are the thing you already learned in first week. Remember the relative motion? I didn't say first week. Sometimes in first exam, right? If you have these two for A and B, right? These two radius RA and RB from this fixed coordinate system XY, right? The relative position from A to B can be written as R B to A. Everybody remember it from exam 1? These things that we learn: relative motion, relative acceleration, relative velocity, all those things. So we'll be reviewing that a little bit again here. Joe, you understand, right? Why? Because of the curvilinear motion and everything, right? The position of these 2 points A, B on a translating body can be related with RB, which is this, is equal to these 2 motions, right? Now, these 2 motions, obviously, this is not linear motion that you are adding. This is the vector term. You understand that? Okay. All right. Now, moving on. These are the vector terms. The absolute position vector, this vector term I would like to highlight here. Okay. Defined from the fixed xy plane, and the vector you can actually not necessarily put only by arrow or line on the top. You can write a bold letter as well. So they use this trick to write the vector RBA. Again, RBA is the position of B with respect to A, and the relative position vector, in other words, between B and A, that is the RBA. And to find the velocity, right? To find the velocity, now I'm going to take out everything here. To find the velocity for this motion BB, you got to find this velocity BA for point A, and then the relative velocity BA, okay, RBA. Now, this RBA value, the relative velocity from A to B, if this is based on a fixed axis, this will become 0, okay? Then these 2 velocity would be same, and the acceleration would be same as well, but you'd like to see it in equation. Let me see. Okay, so they have this thing here. So these velocities and accelerations are the same for what? So when your relative motion RBA is constant with respect to time, okay? With respect to time, all points in a rigid body subjected to a translation move with the same velocity and acceleration. Okay, what does it mean? Try to understand that. Before you do that, let's do the math portion so you're gonna understand it, comprehend it. So you do have this equation, which is RB equal RA plus RBA, right? And then you do the derivative in both sides with respect to time t. So this will become RB, thank you, RB, RA plus RBA. Okay, so here's the thing. If you feel like these are a little bit too much, don't worry about the exam. Try to understand your best, okay? Because this is a take home, only one portion, no homework problem. So you won't be stressed out too much with this topic. This topic is a little difficult, right? I did mention from the beginning. You try your best to understand it, and talk with me even end of the class if you have any issue with understanding anything. All right, so this thing here that we are seeing, RB, the position, RA position, the relative position BA, if you're gonna do the derivative in both sides, the left side would become what? You know that, right? What is the left side would be? The velocity. Very good. Just one second. Something happened. I need to do the escape. It is not working before. Sorry, came back here. All right, so this is the velocity, which is BB. And then the same way, you can do the derivative for both of these. These are the rules for derivative. This will become BA, and this is where the challenge happened, RBA. Now the question is, if you have a rigid body, what does rigid body mean? Say like this RA or RB, these are connecting this way, right? Rigid body means it is not deformed. Understand? So like this is the rigid body. Alright, this is RB, this is not deformed. So the position that RBA, okay, that won't be changing. So if that value is not changing, I can say that value is 0. So that's exactly what they were explaining it here. See? So dRBA dt equal to 0 since RBA is a constant, okay, and all points in the rigid body is subject to translation move with the same velocity and acceleration. So that's the proof they have. So basically all they're trying to say that these velocities are same on a connection like this, right? And if you're gonna do this dV dt derivative one more time with respect to time t, then you'd be seeing it's become the acceleration as well. Okay, so that's another point to understand here. You got it? So you want to write this thing, both this equation. Okay, this is the same thing I'll be writing. So all points in a rigid body subjected to a translational move with the same velocity. So same velocity and same acceleration. You staying class note? All right. Moving on. As I said, I'm gonna go the theory quite a while, because if I'm gonna start with the math, you'll be seeing me doing these things, and you'll be pretty soon get frustrated. What is happening? Okay, so stick with this thing. This is just a warm up. Okay, not necessarily you have to right away understand it by heart. So do the warm up before doing the actual exercise. All right, so the next slide is so important. Take your time. Just basically, but the point to be taken here, these two equations, you just have to understand this. You see, the acceleration and the velocities are same as long as you are dealing with the rigid body connecting rod. In this case, I was giving example. Okay, take your time. I don't want to rush on that. I just have two problems to finish in these 2 days with a little bit of more theory I have. Okay, I know very well I can finish it. Okay, you understand what will happen on Friday though, right? No class. Okay, I'm going to send another reminder email as well. Okay, so nobody will going to show up, but there will be a class that I'll upload it. Okay, in practice space, not the class. It's like a 5-10 minutes video, whatever. I'll talk about the exam, final exam. And you can, during the class time, if you would like, you can, try to reach me in Microsoft Teams. Okay, because that's the class time and I'm not there. So I'm trying to give you all the options possible. All right, it was good. Should I move on? All right, so now we're gonna start with a little bit difficult stuff. Okay, that's called angular velocity. How many of you heard about this angular velocity in physics? Maybe you did heard about it, right? Kind of. Okay, that's the thing we'll be doing now. So angular velocity, let's see if I can highlight that. So this angular velocity is omega. So angular velocity, right? Angular omega. So this omega is related with rectilinear velocity, they call, right? Rectilinear velocity, V. Okay, so that angular velocity omega is related with rectilinear velocity by what? There's a factor. Anybody remember? No? By radius r. Okay. Okay, so if you'd like to understand it on the sketch, I don't want to really draw that sketch again. So see here, if you are interested, you can draw it. You see the omega here? It's a little small in your book. Everybody have the book. Can you see it? You may see it now, right? So this omega here, right? This omega is referring to what? The velocity. And remember, this alpha is referring angular. Joe, you remember the alpha from physics class? Alpha is referring what? Angular acceleration. Alpha is the angular acceleration. The omega is usually the velocity, right? That r is the radius, right? So the rectilinear motion v, the velocity, you can say the usual velocity. If you can assume that a rectilinear velocity is v, that v is related with omega r, right? You see that? And I did started writing it here. In case if you want me to write it here again, I can do it again. So this is my omega and this is my r, right? This is my r, so this is what it is, right? The angular velocity and the relative velocity. So let me write that. So by the way, what is that the movement happen on the angular velocity? Because it's just following one track. How are you going to quantify for angular velocity? Is it the distance that you are quantifying or is it the angle? It's the angle, right? The question has the answer. It's implied, right? So this is the theta, the angle that dictates, right? So then you can write this velocity, the same v velocity, as like d. Sorry. So this v is there. So this angular velocity omega is d theta by dt. So let's go to that, right? Theta is again what? The angle, because we are keeping track it by theta. Okay, so then the next thing that you want to do, angular, that's important, angular acceleration, which is alpha. And just like a or acceleration can be defined as the derivative of v with respect to time t, the same thing is true here as well, right? Derivative of omega with respect to time t. Omega is again what? Angular velocity, right? Now this can be written as this can be written as d theta dt, okay, d omega d theta. You guys agree with me on that? Good, everybody good? All right, so now this d theta dt is, can I write this omega? Why I'm doing all those things? In the math you'd be seeing it, right? So in the math you'd be seeing, like, you would be probably given with the omega equation, and then you gotta do this derivative with respect to theta, not t, because the t was nowhere else given, because the omega could be an equation of theta, not the time. Okay, in that case you have to store this derivative of d omega with respect to theta, and then actually plug all the values for finding the acceleration. Okay, that's something. I mean, there are several steps. I could have go with this chapter several weeks, like, step with these steps with these problems, like finding the angular acceleration, finding the angular velocity, and all sorts of things, right? The fundamental stuff first, and then slowly jump into the application. Obviously, I'm not doing it for this chapter. We're going to do just two problem with applications. Okay. Any questions so far? Everybody understand the alpha and everything? Okay. This alpha, I'd like to put a mark here. This thing, I'm going to put a mark here. You'd be needing them. Okay. So then a few more equations I'd like to give it to you. Very important, which is, what if the alpha value is constant? So you can say as a subscript C, alpha again is angular acceleration. So what if this is a constant? So if this is a constant, then can I use this equation that we learned in exam 1 here as well? So like alpha is equivalent to the distance. Remember, we had this as equal the final distance s plus a t when a is constant. You remember this equation? Okay, so I'm going to write few more equations. See if you can write those equations here for angular parameters, right? The other one, I don't know if you remember, like, sorry, this was not s, this is v. The other one is like s equal to s0 plus v0t plus half of at square. You remember that projectile motion, the y distance equation, right? We oftentimes use this. All right, so this s, I'm using it a generalized way, so it x or y, whatever way the movement happen. Okay, so then you guys remember this, you guys remember the equation that we can use it for projectile motion. Why we were able to use this y equation for projectile motion? You remember that, right? Because the projectile motion experience the gravity. What is the value of the gravitational acceleration? 9.2. Does the value varies? No, it's a constant. You see, when the acceleration is constant, we can use this equation, right, Christian? So you understand? It doesn't make sense now why you were able to use that equation. Okay, when the acceleration is constant, did you got it? When the acceleration is constant, you can use this equation. So in projectile motion, do you remember we use this y equal to y0 plus this thing? The why we use that y equal to y0 plus this thing, because you see the gravitational acceleration g is constant. Okay, if that one is constant, the same things goes here. We can write s equal to s0 blah blah, because the a is constant. Okay, moving on. So I have another equation. So like v square equal v0 square plus 2 of a s minus s0. Okay, where let me give you the other values. So s0 and v0 are initial. You can say this initial. Since these are nodes, I'm going to try to separate it properly. This is side node, right? Or you can say nodes. Don't get confused with those equations that I'm writing, okay? Initial position and the velocities, right? The writing gets a little distorted, not because of my writing, this is the pen. Now, I did write this equation. You did use it in exam 1, right? Can you rewrite those for theta, theta 0, omega, omega 0, alpha, and t time t? Can you rewrite those? So basically, I'm saying rewrite this equation for theta. These are the terms that you're going to be using. Okay? Omega 0. Can you rewrite that? Instead of A, alpha C. Why I'm using alpha C? Alpha is for angular acceleration whenever I have a subscript C that is coming from the constant, right? So as if like we're knowing that already, that alpha is constant. See if you can write that. Okay, I'd like to do a walk around and see if you can write these three equations by using those terms for angular velocity, angular acceleration, angular position. Do that. That is a good way of thinking the whole thing. Repeat that. Get that? Okay. My goal is to finish this theory today and a little bit more, and then start with just the math. Like first math. Just start with that. Okay. Obviously, there's not enough time to finish it. And the thing is, like doing one problem is is not enough for the 50 minutes. We are done always well before, and doing two problems is a little bit tricky always. It's kind of very difficult to finish. Like last class you've seen, right? Last class we barely finished it, the second problem. You got it, right? I'm assuming. Let me write it and see if it matches with yours. Okay. So you should have, let's start with the first one. Omega equal omega 0 plus alpha ct. This is the first equation, right? And then you should have theta equal theta 0 plus omega 0 t plus half of alpha ct squared. This is the second one. You got it? The third one would be omega square is equal omega 0 square plus 2 alpha c theta minus theta 0. You got it? All right. Then I have one final thing to cover and then I'll be done with this theory, okay? This is the, remember the normal acceleration and tangential acceleration, right? How those are related here. with angular acceleration. That is the final thing that I'll be covering, and then there's nothing more on this chapter. Okay, everyone understand this and feeling confident with this? Okay, perfect. And then we're going to be focusing here, okay, slowly. And these are the equations that I was talking. Okay, these are the equations that I was talking all those things. One thing, that the last thing that I'd like to give you the understanding, which is the direction, right? The right hand thumb rule. Anybody heard about this thing from physics class before? Right hand thumb rule. So what the right hand thumb rule means is, like, if the, see, any motion that can happen clockwise and anti-clockwise, right? So if the motion is clockwise, I did explain it in statistics class as well. Remember right hand thumb rule? So I, J, and K, whether it should have like plus and minus, right? Multiplying the cross product and dot product. Remember the cross product, I cross product J is like K is positive, right? But J cross product I is what? K is negative, just because of the right hand thumb rule, right? What it means, depending on the motion, if it is clockwise motion, right? So like this way, from my end, right? If it is a motion like this, this is the positive direction. If it goes the other direction, is the negative direction, okay? So that's what it explained here. Please read through that from the book. I did cover it before, that's why I'm kind of skipping that. Any question on that? The direction? Okay, very good. Now this is the point that I'd like to focus more here. Okay, so this is the point. So first of all, everybody know this equation, like the magnitude of acceleration vector, right? So that's everybody knows. But thing that is new to you, which is the normal acceleration an and tangential acceleration at, can be defined by these two equations. In other words, let me write it. So normal acceleration an is, what is the normal acceleration an? Anybody remember? V squared by rho. What is rho again? It's the radius of curvature, as if like you are talking about the radius, right? So is this the same radius that we are kind of seeing, the omega and the r? That's the radius, right, Joe? So can I write instead of this rho is the radius of curvature. Joe, you remember that? So can I write this instead of rho r, right? This is the same thing, right? If it's a circular motion, why do they use the rho? Anybody remember? Why do they use the rho? Why they even bother using the rho? Because all the curvilinear motion not necessarily is a circular motion, right? Curvilinear motion could be anywhere, right? Make sense? So any part of the curve that we are dealing, that part is its own rho or own radius of curvature. Make sense? That's why we use the rho. Here we are not using it. We have the explanation based on a circle, and the r is the radius. Now I'm just trying to deduce something here. You guys remember the v, or velocity, can be written as omega r? Everybody remember that? It might be in your classroom already, right? Can I do this thing like omega r square on the top, and then you have this omega square r square, and this r and square is going to cancel out. So can I write this thing omega square r? You see that? So again, I'm rewriting the same thing. An, or the normal acceleration, is I thought it's omega square r. Yeah, omega square r. It's omega square r. Now, in my notes, it's written wrong. So it's omega square r, okay? And then the tangential acceleration. So tangential. What is the tangential acceleration? At. Anybody remember? Is it like dv over dt? That's the velocity that we are talking. So if we say dv over dt, so what is the alpha again? Can we remember the alpha? Is it like d omega by dt? Right? That's what we learned, right? There's the angular acceleration. Okay. So now can you deduce this and find this thing alpha r? Do that. In other words, what I'm asking, maybe looking confusing, dot means your work. And you should be finding at equal to alpha r. Can you do that? See if you can do that. Okay, and this is a very straightforward thing. I know everybody can do that for sure, right? It should be, because you have this omega r, right, then dt, and then you'd be doing r, this r with respect to time t. Do you think like the r will gonna change with respect to time t? The radius will not gonna change, right? So then you have this d omega dt and this r by alpha. That's your at. So that's the equation that I'm writing. Okay. So far, everybody's with me. I didn't lose anybody. All right, perfect. So then let's deduce a little bit more. What is this a again? This a, or acceleration, has two parts, right? Obviously the normal and the tangential acceleration, right? So let's deal with this a again. So this a does have this two part, dw dt multiplied r plus omega dr dt. In this case, what I'm doing here, I'll be assuming these two quantities here. This r is, this is a different case, okay, where r is fixed. In this case, I'm assuming this r is not fixed. What is happening if the r is not fixed? In other words, you are dealing with a situation where you have a curvilinear motion. You are not dealing with a circular motion. It makes sense? So then you remember the product rule for derivative. So like, let me give you a reminder. So like dab dt can be written as a dv dt plus, remember the product rule, da dt. That's what I did. Does everybody understand this? All right, so if you understand this, in other words, that's a special situation for tangential acceleration that I wrote. And then you can rewrite this as, this is alpha r plus, this one is omega, and this one can be written as dr dt can be written as omega rp. How? Or r? How I can do that? I told you it's gonna get a little bit complicated soon, right? This is the time when it gets complicated for the derivation only, but you don't need to necessarily need to use this derivation all the time. You just need the final answer. I'm gonna derive you the final answer, okay? So in case if you lost at this point, it's all right, because this is just the derivation, okay? Okay, so I'd like to highlight something. So you see, dr dt, okay, so dr dt can be written as omega r. So omega multiplied r. So then you have this vector a. Now this omega r, if you're gonna do this, this is a cross product and this is all vectors, okay, and there is another cross product here. So if in this part, as I said, like getting a little bit complicated, and this r is again the vector here, right? So this is vector, all those vectors here, right? And this a is also vector here. So then this whole thing can be written as a alpha product r, okay, minus omega square r, okay. So in other words, it can be written as at plus an, okay. Bottom line, if you are dealing with this vector product, then you can write this thing this way, but the magnitude, that's what's so important. You need to oftentimes find the magnitude of total acceleration. So at square plus n square. I guess this is all it matters. You just have to remember these, okay? And you just have to remember these two equations that I wrote it separately. All the box term, that whatever I had, okay? The derivation part, I don't know. I don't want to go through I don't want to go through that thing again. So some of the snapshot is here, as you can see, for vector. Just read through that if you're interested further. But as I was saying, like we're gonna simply using this equation now. We are obviously running out of time, but just want to give you a quick overlook what we'll be doing in next class. Okay, so we'll be solving this problem. A motion, see there is a gear setup here, right? Do you see that? A motion turns gear A with a constant angular acceleration alpha, okay, for this alpha, this value. All right, and another thing, just to highlight here, they don't use degree, they use radian. You guys remember the relationship of degree and radians, right? All right, so yeah, pi by 180, right? Pi is 3.14 something. The cord is wrapped around the pulley. No, don't worry, I'm not going to solve it. I'm just reading through the problems. The cord is wrapped around the pulley D. So there is the cord, as you can see, which is rigidly attached to gear P. So this pulley D and B and D are fixed. So B and D are fixed, okay? So that's the problem. You got to find the velocity of the cylinder C. So there's this cylinder C is hanging here. So you got to find the linear velocity V here, right? And it travels in 3 seconds. So the time value T is given as well. In 3 seconds, how much of the distance it travels, okay? So these are the things that you got to find. Not that difficult problem, not that easy either. You got to have to use all those equations that I'm showing it to you. Hopefully the Wednesday class will be exciting for you, as long as if you understand all the equations that I had, at least the bare minimum, the angular acceleration and the velocity, and then I'm gonna make it available to you. I believe I make it available on Friday. Now, yeah, I think I make it available on Friday because this exam is due on Wednesday. I don't want to make it available on Wednesday and a week for the exam. Usually people don't give that much time, right? 2 days weekend, but you have until Wednesday anyway. Okay, but again, on Friday class, 2 things will be available to you: 1, 5, 10 minutes, 20 minutes, whatever the lecture will be, where I'm be talking with the exam itself. That video will be available to you, and then you'll have the exam available to you, and you can reach me as I was saying, like in Brightspace, not Brightspace, in Teams, Microsoft Teams, if you have any question. Okay, all right, that's it. I'm gonna see you around.